Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the third element in the periodic table, the explosive element lithium. I have a sample of lithium in this little vial right here, and it is so light I can barely tell it's even there. Let's get back to our slides. Here, we see the beautiful periodic table produced by Theodore Gray. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to pick up. Check out his fantastic website, periodictable.com. As I mentioned, lithium is the third element in the periodic table. Its atomic number is 3 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. José Bonifácio was a Brazilian scientist and statesman who first described a new mineral in 1800 that turned out to be a chemical form of lithium. He studied with, among many others, Antoine Lavoisier and Alessandro Volta. He traveled extensively through France, Germany, the Netherlands, Scandinavia, Bohemia, Hungary, Turkey, and Italy. It was on the Swedish island of Utö he made his discovery. And it was this mineral he discovered. It's called petalite and is a lithium aluminum silicate. 17 years after its discovery in 1817, Swedish chemist Johann August Arfwedson was able to isolate pure lithium salts, but he failed at his attempts to isolate the actual metal. He also discovered lithium's presence in two other minerals, spodumene and lepidolite. Arfwedson worked with Berzelius, often considered one of the founders of modern chemistry, and it was Berzelius who suggested the name for the new element. From the Greek lithos, meaning stone, Berzelius suggested lithium, since it was refined from a mineral. German chemist Christian Gmelin was the first to observe the brilliant red color given to a flame when lithium salts were introduced to the fuel. Lithium metal was finally isolated in 1821 by William Brand using electrolysis of lithium oxide. The metal was soft and shiny but corroded quickly when exposed to the atmosphere. Here's a look at nice, pure lithium preserved under oil to keep it from oxidizing. Note that it's floating. The element lithium is the 44th most common element in the universe, still making up only 6 parts per billion of everything. A bit more about that. Lithium is one of 3 elements made within 20 minutes after the Big Bang. But as you can see, not much lithium was made at that time, only 1 atom of lithium for every 6 billion of hydrogen. Given that the sun is made from the same stuff as the universe, you'd think the sun would have the same proportion. But stars are lithium-destroying factories. There's 1/100th as much in the sun, 6 parts per 100 billion, compared to the rest of the universe. Lithium is the rarest element in the sun, the 74th most common. It's the 35th most common element in meteorites, with 1.7 parts per million. Like meteorites, it's also the 35th most common element in the crust of the Earth, 10 times as common as in meteorites at 17 parts per million. Because of its highly reactive nature, it's never found in its native metallic state, only in compounds. The oceans also contain a small amount, at 180 parts per billion. It's the 17th most abundant element there. And lastly, there is a bit of lithium in us, about 30 parts per billion, 36th out of 41. This complicated version of the periodic table shows the evolution of the elements through the history of the universe. Here, you see each element square with a tiny chart of its own showing that element's growth over the age of the universe by various processes. Lithium is here. I understand this looks complicated, but I want you to notice that lithium is one of three elements, hydrogen, helium, and lithium, that are primordial elements. Those elements have white backgrounds. They were created in the Big Bang. Let's look at just lithium a little closer. The horizontal axis of this square represents time from the Big Bang to now. The vertical axis shows the proportion of lithium created by various processes. The majority of lithium present today was created at the time of the Big Bang, 13.8 billion years ago, and again is called a primordial element. For the first 3 minutes after the Big Bang, the universe was too hot to form protons or neutrons, so there were no elements at all. At 3 minutes, the universe had expanded and cooled enough to form mainly hydrogen and helium nuclei with a smattering of lithium, but was still too hot for electrons to stay associated with atoms. It would take another 370,000 years or so for the universe to cool enough for neutral atoms to form. In our lithium square, this is represented by the white area. A small part has been distributed by supernovae, the yellow sliver on the top, and some is redistributed by dying low-mass stars, the magenta area. Nova Delphini 2013 is the first nova that has been observed to synthesize the element lithium. This is the first direct evidence of an astronomical object supplying lithium to the interstellar medium. It's hard for lithium to exist at the center of a nova, but the fact that lithium is blown out by the force of the nova was observed by astronomers here. Nucleosynthesis of lithium is important in the study of chemical abundances in the universe. In a nova, the star has run out of hydrogen and starts burning helium. Here's how that works. Inside the star, it's much too hot for the atoms to hold on to their individual electrons, so we're dealing with nuclei. The electrons are still there, but just part of the general plasma. We start with a helium-4 nucleus with 2 protons and 2 neutrons. We also have helium-3 nuclei with 2 protons and 1 neutron. These collide with each other and fuse, making a beryllium-7 nucleus with 4 protons and 3 neutrons, same as our initial ingredients. Now, the beryllium nucleus is hit by an electron, turning one of the protons into a neutron. 3 protons means our atom is now lithium-7. The production of lithium-7 from beryllium-7 was observed by the astronomers in the wind blown out of the nova. I was just talking about lithium-7, but it's only one type of lithium. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same, 3 protons for lithium, but there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They're chemically identical to each other, but with slightly different weights. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 9 known isotopes of lithium, and of these 9, there are 2 stable, non-radioactive isotopes, lithium-6 and lithium-7. These 2 isotopes make up these percentages of naturally occurring lithium in the universe, the majority being lithium-7. By the way, the word isotope comes from the Greek isos, meaning same or equal, and topos, meaning place, since all these various forms of lithium occupy the same place in the periodic table. All of the radioactive isotopes of lithium are very short-lived. More on half-life in the next slide. I even hesitate to show you these. The longest-lived isotope is lithium-8, with a half-life of only 839 milliseconds, less than 1 second. Some of the half-lives are measured in time units most people have never heard of. The ZS stands for zeptoseconds. A zeptosecond is a billionth of a trillionth of a second, 10 to the minus 21 seconds. And YS stands for yoctoseconds, a trillionth of a second, 10 to the minus 24th seconds. Light, moving at nature's speed limit of 300,000 kilometers per second, cannot travel across even 1,000th of the diameter of the lithium atom in a yoctosecond. I don't even know how one would go about measuring such a short half-life. I suspect these are calculated. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1,024 atoms of any isotope from the previous slide, even the short-lived ones. If you wait one half-life, half of your isotope will decay, and you'll have 512 atoms left. If you wait one more half-life, half of that half decays, leaving you with 1/4 of the original 1,024, or 256 atoms. Another half-life, half again as many, or 128 atoms, and so on. Just keep dividing by 2 every half-life. After 10 half-lives, you'll have about 1/1000th of your original amount. By the way, notice there's one remaining atom here after 10 half-lives. If you waited one more half-life, your remaining atom would have a 50-50 chance of decaying in that time. Lithium is part of a group of metals that sit along the west coast of the periodic table called the Alkali Metals. We'll leave hydrogen out of the discussion here since it's neither a metal or a solid. All of these metals are highly reactive, and some are explosive when submerged in water. They're very soft, too, so soft you can cut them with a dull butter knife. They also have a similar electron configuration in their outer shells. Here we see the electron configurations of the alkali metals. Notice that lithium, sodium, potassium, rubidium, and cesium all have a single electron in their outer shell. Lithium is really, really light, as I previously mentioned. Its density is only 0.534 grams per cubic centimeter, about 1/2 that of water at 1 gram per cubic centimeter. That's why it floats. I've put up a few more elemental densities so you can compare. Note that lithium is less dense than any of these. Don't believe me about lithium floating in water? Watch this. See it floating? Of course, lithium is highly reactive and produces bubbles of hydrogen gas. It gets very hot during this reaction and usually melts into a liquid itself. Unlike its cousins in the alkali metal column, it does not explode in water. The lithium reacts with the water, creating lithium hydroxide and hydrogen gas. Let's compare its density with the rest of the elements. Here is a graph of the elements from highest density to lowest density. When I do this talk with an actual audience, I have a set of blocks so you can feel density for yourself. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, to magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, lithium's density is 0.534 grams per cubic centimeter, the magenta circle slightly above that horizontal row of gases. As you can see, lithium is the least dense element of all the solid or liquid elements. Only gases have lower densities. Lithium melts, or conversely freezes, at 180.54 degrees Celsius, or 356.972 degrees Fahrenheit, near the bottom of the chart. Only 21 elements have lower melting points, and that includes 10 gases. It boils at 1,342 degrees Celsius or 2,447.6 degrees Fahrenheit. That's 1,161 degrees Celsius above its melting point. That's a middling liquid temperature range among the elements. If we compare the size of the lithium atom to that of hydrogen, we'd see something like this. The lithium atom is a little over 3 times the size of hydrogen. Lithium and the rest of the alkali metals on the left side of the periodic table all have large atoms because they only have that one loosely held electron in their outer shell that they would dearly love to lend to another atom, leaving their electron structure very much like the stable noble gases in the right-hand column of the periodic table. We'll come back to this in a couple slides. By the way, a picometer is a trillionth of a meter, so atoms are very, very small. Here are atom sizes sorted from largest, cesium on the top left, to smallest, helium on the bottom right. Lithium has a slightly above average size atom, but it's the smallest atom of the alkali metals, which I've marked in blue here for you. If we rearrange the previous chart, we get another interesting look at atom sizes. In this graph, like the previous one, the vertical axis is the size of the atom, but the horizontal axis is the atomic number of the atom, the number of protons in the nucleus, starting with 1 for hydrogen and going up to 86 for radon, with hydrogen on the left, which I'll also label in red on the periodic table. We see patterns. The alkali metals, the yellow labeled elements found in the leftmost column of the periodic table, all have large-sized atoms because, as I mentioned, they all have only one loosely held electron in their outer shell. The magenta-labeled noble gases in the right column of the periodic table have very tightly held, full outer electron shells. These are the smallest atoms in their respective rows. Again, notice lithium with the smallest alkali atom I've relabeled in blue and also on the periodic table. Lithium is a relatively inexpensive element. It goes for about $83 per kilogram, and you get a lot of lithium in 1 kilogram because of its low density. Of course, price depends on the quantity you buy and its purity. This price is for 99% pure lithium. Lithium's price was relatively stable until 2021, when its price went up by a factor of 8. This may have been partially pandemic-related, and this year, 2023, the price has fallen to 1/2 of the 2022 prices. As you can see here, lithium production really took off in 2017. Given all its uses, as we'll discuss in a moment, this trend is likely to continue. It looks like the production continued through the pandemic, which argues against my hypothesis of the price increase in 2021 and 2022. Most of the lithium reserves are in Chile, followed by China, Australia, Argentina, and everyone else. Australia is clearly the largest current supplier of lithium, with almost 1/2 of the world's production, followed by Chile, China, and Argentina. The rest supply a minor amount, only 4%. Given the strategic importance of this element, the search is on for new sources, and this chart may change. One of these new places is the Salton Sea in Southern California. California's drought conditions have exacerbated an ecological nightmare at the Salton Sea. Already twice as salty as the ocean that created it, fish and bird species are threatened. Toxic dust from the dry lakebed is threatening the health of people who live nearby. However, out of these problems may come an opportunity. The Salton Sea sits directly on the San Andreas Fault. Geothermal activity in the area drives lithium compounds to the surface. Several companies will extract the superheated brine from the ground, generate electricity, which will then be used to separate lithium, sodium, and calcium. It's possible that 600,000 metric tons of lithium carbonate per year will be produced at this site. Enough that it's being called the Lithium Valley, in a nod to our Northern California Silicon Valley. Even with all those suppliers and possibilities, lithium is considered an endangered element. It's industrially essential and yet is of limited availability. So let's take a look at a few applications of lithium. As you can see from this chart, the 800-pound Pac-Man in the room is the use of lithium in batteries. 65% of the lithium supply is dedicated to this use. About 1/5 is used in the ceramics and glass industry, 5% for lubrication, 3% for continuous casting, and 9% for everything else. Sony made the first commercial lithium-ion battery in 1991, and today they come in all shapes and sizes, as you can see here. Although it's too much to go into in this presentation, a lithium battery is basically a sheet of aluminum covered with a lithium compound, a sheet of copper coated with a graphite compound, both separated with a sheet of material that can let lithium ions through while insulating the copper and aluminum sheets from each other. The sheets are often rolled up to make a convenient package. I leave it as an exercise to the student to look up how this functions. There are several variations on this battery. Lithium powers almost all our personal electronics: phones, hearing aids, cameras, laptops and tablets, watches, just about everything. Lithium batteries also power our electric vehicles. The batteries are light in weight, can be recharged thousands of times, and have a high energy density, meaning they can contain a lot of energy for their size and weight, the perfect mixture for a car. Perhaps you have solar panels on the roof of your home or business. Those work well when the sun is shining, but they don't generate power at night. The same goes for wind power, which only generates power when the wind is blowing. If you add a lithium battery pack to these systems, energy generated during the day or when it's windy can be stored and used at other times. You could be independent of the electric grid. However, if you stay connected, once your batteries are charged, you can sell your excess generated energy back to the power company and help pay for your installation. The second largest use of lithium is in the making of ceramics and glass. Lithium adds certain critical qualities. First and foremost, lithium is the component responsible for making glass and ceramics have very low thermal expansion. This is especially important in many applications. If you have a glass cooktop, it must not expand when heated. If the glass over a burner expands more than the glass surrounding it, the top would shatter. Likewise, the glass of telescope mirrors must not expand or contract with temperature, or the optics will change. This mirror, seen before the reflective surface was applied, was flown on NASA's Kepler mission, which has detected thousands of exoplanets. If you have a ceramic crown, like the one in the middle here, you probably have a lithium compound in your mouth. These are carved from blocks of lithium-containing ceramic, like the ones you see here. In addition to its low expansion rate, important to keep your crowns from popping out if you drink a hot beverage, the lithium helps ensure color consistency and improves durability. Most lubricating greases are mixtures of an oil and a soap. The soaps are dispersed into the oil and make them into a viscous and stable gel we call grease. Grease made with lithium soap, or lithium grease, adheres well to metal, is non-corrosive, may be used under heavy loads, and exhibits good temperature tolerance. Here we see the dear leader imparting his knowledge to guide the grease factory to a glorious future. To be totally honest, the grease production does have an aesthetic quality about it. However, I wish I could muster the enthusiasm shown here. It was popular to go to lithium-containing springs, such as here at Lithia Springs in Ashland, Oregon. You can see that the springs contain some level of lithium bicarbonate. People's outlook on life was said to improve after drinking water from these springs, no doubt due to the lithium, as we'll see in a few slides. Here you see a diagrammatic cross-section of a hydrogen bomb. The hydrogen part of this weapon is lithium deuteride. The hydrogen here is a heavier isotope called deuterium. It's contained in the so-called pencil at the center of the bomb. During the fusion process, the lithium is converted into another hydrogen isotope, tritium, which then also participates in the fusion process. The lithium deuteride is the fusion fuel that takes a normal atomic fission bomb to the next level of the much more destructive fusion bomb. Hydrogen bombs started out the size of army tanks and have become small enough to fit in the trunk of your car. The largest ever constructed by the United States, called Castle Bravo, was tested March 1st, 1954. It was the size of a small building. It carried a big wallop. Castle Bravo yielded 3 times the explosive power it was designed to yield. 15 megatons instead of 5 megatons. Lithium played a central role. Let's travel to the location of the Castle Bravo test, Bikini Atoll, and see what it looks like today. Looks like it would be a great place to snorkel. Unfortunately, it's still uninhabitable because of the radiation. You can still see the crater left by Castle Bravo. It's over 2 kilometers in diameter. We've already seen the red color given to a flame when you add lithium salts. It's also used in fireworks to give them a red color. Strontium is another element also used to color fireworks red, but with a slightly more orange tint. There you see the red color of lithium. Returning to consumer goods, in 1929, Charles Leiper Grigg invented a drink he named Bib Label Lithiated Lemon Lime Soda, which eventually became 7-Up Lithiated Lemon Soda. Why the original name was so unusual is a mystery, since his previous sodas were named Whistle and Howdy. No doubt the lithium citrate and its antidepressive effect helped keep his customers happy with the product. That ingredient was removed in 1948. It's been suggested that the atomic weight of lithium, 6.941, or very close to 7, is the reason it's called 7-Up. In 1948, Australian psychiatrist John Cade was the first to use lithium in the form of lithium carbonate to treat and prevent episodes of mania in people with bipolar disorder. Lithium is also sometimes used to treat depression, schizophrenia, disorders of impulse control, and certain mental illnesses in children. Your body may use lithium as a micronutrient necessary for maintaining health, though this is still under study. For most people, a healthy diet, or even tap water, should meet daily requirements, so no need to take lithium supplements. We'll end this talk with Mary Soon Lee's elemental haiku about lithium. Lighter than water, empower my phone, my car, banish depression. In the next program in this series, we'll examine the lightest metal you can actually hold safely in your hand, beryllium. I hope you'll join me. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about the element lithium.